In this example, a child has tied two cars together with a string, and the child's pulling on the front car with a force of 3.2 newtons. The mass of each car is given in the diagram, and the question is, what's the acceleration of the system, and what's the tension in the string that connects the cars? And you're allowed to ignore friction in this problem. Now this is a slightly harder problem than the ones we've done up to this point because we have two objects to worry about. But let's take the same approach we always do. First, let's consider all of the forces involved. Let's think about the horizontal dimension first. What forces are involved in the horizontal dimension? Well, looking at the rear car, the red one, there's really only one force pulling in the horizontal dimension, and that's the tension from the string. The string is pulling that red car along. Alright, what forces are acting horizontally on the green car? Well, think about it. The string is dragging the green car back. Whatever tension is pulling the red car forward is actually pulling the green car back. So that's a force that's horizontal acting on the green car, pulling it to the left. Of course, the child is pulling the green car to the right with a force of 3.2 newtons. Those are the only forces acting on the green car horizontally. And in fact, those three forces make up all of the horizontal forces in this problem, since we're ignoring friction. There are some vertical forces, however. The weight of the green car is pulling it down, and to keep the green car from falling through the floor is pushing up with a normal force. The weight of the red car is pulling it down, and to keep the red car from falling through the floor is pushing back up with a normal force on the red car. Those are all the forces acting in this situation. Well, there are a lot of forces in this problem. How do we deal with them? Well, we first must realize that the laws of physics have to work for each individual object. So if I look at this situation, what I can do is treat each individual car by itself. So let's just look at the red car for a minute and act like the red car is the only thing in the problem. The red car has three forces acting on it. The tension in the string is pulling it to the right, the weight of the car is pulling it down, and the floor is exerting a normal force up to keep the car from falling through the floor. Alright, let's concentrate on the horizontal dimension because that's where the action is. In the horizontal dimension, the sum of the forces have to equal mass times acceleration. There's only one horizontal force here, T. We'll define motion to the right as positive, so that T is positive, and so the sum of the forces is simply T, and that has to equal the mass, which was given, the mass of the car is 3.5 kilograms, times the acceleration. Well, here we are again, back in familiar territory. We've got one equation here and two unknowns. We don't know T, we don't know A. So we can't solve this equation yet. However, we do have another object to consider. Let's go to the other object and see if we can find another equation to help us. Well, the other object is the green car. Here's the green car and all of its forces. Now remember, the action's in the horizontal dimension, so that's what we'll concentrate on. And remember, I've already defined motion to the right as positive. So there are two horizontal forces here. The force with which the child is pulling, 3.2 newtons, and the tension. Now remember, I've already defined motion to the right as positive. So the 3.2 newton force is a positive force. So the sum of the forces, once again, has to equal mass times acceleration. The sum of the forces would be positive 3.2 newtons plus a negative T. T is negative because it's pulling in the negative direction. The sum of those two forces then has to equal mass, which is 4.5 kilograms, times acceleration. Well, once again, we have an equation here that has two unknowns. However, remember, we learned something from the red car. We learned that tension is 3.5 kilograms times A. Let's go ahead and stick that in for T in this equation. So we have the 3.2 newtons plus negative 3.5 kilograms times A equals 4.5 kilograms times A. Now we have one equation with one unknown, and we can solve for it. When we solve for A, we find that A equals 3.2 newtons, which is a kilogram meter per second squared, divided by 8.0 kilograms. Kilograms cancel, and we find that the acceleration is 0.40 meters per second squared. It's positive because this whole system is accelerating to the right. Now we're not quite done because the problem also asks for the tension in the string. Well, we have an equation for tension. The tension is 3.5 kilograms times the acceleration. We now know the acceleration. So the tension is simply 3.5 kilograms times 0.40 meters per second squared, or 1.4 newtons. Alright, so those are the answers, but before we leave this example, think about what we did. Most of what we did here is what we've been doing for the last two modules. We sum up the forces, set it equal to mass times acceleration. However, the key to solving this problem is to realize that we could treat each car independently. That's true in all of physics. If I've got a system that has multiple components, the laws of physics have to be obeyed by each component. So I can treat each component independently. Each component gives me an equation, and if I look at all the equations, I should be able to solve them simultaneously to get all of the answers.